my program from last class. If you remember, we used the arcade-4 method to numerically solve the damp-driven pendulum. And in doing that, we had defined the RK4 method for calculating the value of the function at a time interval I+1, say, from the value of the function at a previous time, I, and the function's derivative. So that's this first guy here. We've seen this a few times now. And then we had a second user-defined function. I called it pendulum, and it was the one that described we broke the second order differential equation down into two first order differential equations, one for angle, one for the rate of change of the angle, and one for the rate of change of the angular velocity. And this function defines those two rates of change of the angle and rates of change of the angular velocity. So here's the rate of change upstairs here of the angle, and then these two guys here really represent that, these three guys represent the terms in that second order differential equation, which we can think of as the rate of change of the angular velocity. So in here you see the term that arises from the restoring force, the term that arises from the damping force, the term that arises from the driving force. Okay, so now I've got my parameters that are describing the discrete time that I'm working in. I'm going to look at 50 seconds of this oscillating pendulum. Remember, its period is 2 pi seconds, so a little over 6 seconds. I'm dividing that into 2,000 time intervals. So that's my discrete time. And then I got the parameters of the pendulum. I made L like G 9.8 meters, and G is 9.8 meters per second squared. That means that my natural frequency, which is square root G over L, is just going to be 1 radians per second. So that's the 1 radians per second. And then I've got 3 more constants associated with those features of damping and driving the pendulum. The damping constant, I'm going to switch that off to begin with. Then the amplitude of the driving force, and then the frequency of the driving force. I switched off the driving force right now because alpha's 0. And then I got my initial conditions. I'm just going to release my pendulum from rest, having displaced it by 1/10 of a radian, so a handful of degrees. And so now I'm going to do the calculation of the function, the solution to the second order differential equation, based on the initial conditions, the 2 initial conditions. So here's where I solve for the function using the RK4 numerical method. I'm going to make 3 plots. So 2 of them we did last class. So theta versus time. That's from my numerical solution. Angular velocity, omega, versus time. So those are the ones from the last class, and then the new phase space plot. And let me take this little slicing out to begin with. I'm just going to plot not theta versus time or omega versus time. I'm going to plot theta versus omega. So that is the phase space. That describes the state of the system. And in this portrait or this plot, we can see the evolution of this system. We can see the phase space trajectory. And so, wish I could make this go away. These are the 3 plots then. Upstairs here is angular displacement versus time for my 50 seconds. Remember, my amplitude was 0.1 radians, so it's oscillating backwards and forwards periodically. Here's my angular velocity. in radians per second. You notice it's out of phase. So when the angular velocity is 0, you're at maximum displacement on the negative or positive sides. When the angle is displacement is 0, so you're at the equilibrium point, you got the maximum angular velocity. So these two are out of phase. And if you plot the angular displacement horizontally here versus the angular velocity, you get this phase space diagram. So this describes the evolution of the states of the system. You'll notice this diagram, it has both theta and omega in the diagram. So it describes the states of the system, but it doesn't explicitly have the time in this diagram. So it is a difference. If we were to watch it as a function of time, you'd see the you'd see the state in phase space. We would be starting over here on the far right. That was our initial angle, and our initial velocity was 0. So we'd start here, and then we would run counterclockwise around this oval, or around this ellipse, and that would be our trajectory through phase space. That's the pendulum's trajectory through phase space. Is that phase space diagram fine? It's going to get worse. Okay, so that was straightforward, I think. So I want to look at damping now, and we can see what damping looks like on a phase space diagram. So I'm going to go back upstairs here, and I'm going to switch on damping, and I'm going to go through these 3 cases of underdamped, critically damped, and overdamped. So this is 0.1, and this is in units of the natural frequency, and so 0.1 is underdamped. And so here's the 3 plots for the underdamped pendulum, right? So upstairs here, you see the plots from the last class, their angular displacement, angular velocity. You see that the pendulum's motion, pendulum's energy is dissipating, the pendulum's motion is decreasing. As we turn the kinetic energy of the pendulum, it gets dissipated, say, as into heat energy. So those are the familiar plots from the last class. If you plot angular displacement horizontally versus angular velocity vertically, you get this spiral here. And now it's probably a little clearer how this represents the phase space trajectory of the damped pendulum. So we are starting over here on the far right-hand side. Our initial coordinates were that the angular displacement was 0.1 radians and the angular velocity was 0 radians per second. So we start here, and then we swing back through the equilibrium point here, swing over to the left-hand side, negative angle coordinates over here on the left, and then we return. But this time we don't just return along the same path as we did when there was no damping. This time we're returning on a path of smaller amplitude, of smaller maximum angular velocity, and we spiral inwards until finally the pendulum will come to rest as we're dissipating energy, and finally the pendulum loses all its energy. And so this is a phase space plot for the case of an underdamped pendulum. And if we were to change that parameter beta, if we were to say make it even smaller, make it 0.05, 2 times smaller, then this would be a spiral of many, many more revolutions. If we were to double it, then there would be more dampening. Then this would be a spiral with less number of revolutions until we dissipate all the energy. So a special case, we said that if you work for Ford or you work for Toyota, then you know this case well, critical damping. This is when you want to damp out mechanical vibrations as fast as possible. This is when beta in units of the natural frequency is 1. The damping constant equals the square of the angular velocity. This equals the square of the natural frequency. And so here are the 3 plots for that case. So again, upstairs, angular displacement and angular velocity versus time. We see that relatively quickly, within 10 seconds of this 50 seconds, the pendulum, we've displaced it, is kind of just relaxed back to the equilibrium. It didn't oscillate back to the equilibrium, going to and fro. It just smoothly relaxed back to the equilibrium. And you can see this on the phase-space plot down in the lower panel here. Right, we start out at this position on the far right. So this is 0.1 radians displacement in the positive angle direction, released from rest, released with 0, angular velocity 0. And then it picks up some speed and starts moving back towards the equilibrium point. And here it's approaching, after 10 seconds, it will have reached that equilibrium point. This is 0, 0. It's at the equilibrium point. It's got no angular velocity. It didn't swing through that point. It didn't oscillate around that point. Critical damping, it just relaxes to that point. Let's do one more. So this is 10 for the damping constant. So that's the case of overdamping. Overdamping, like critical damping, does not involve oscillations. Only underdamping involves oscillations. Critical damping is the fastest way to get back to the equilibrium, to damp out the vibration. Overdamping gets you back to the equilibrium point without oscillations, but at a slower rate. Okay, so here are the 3 plots in this case. So again, of course, same order: angular displacement upstairs, angular velocity in the middle, phase space down the bottom here. So you see from the angular velocity and the angular displacement, the top 2 plots, that we start with the pendulum displaced from the origin with 0 velocity. It then starts to swing back towards the equilibrium. But it's taking a long time to get to the equilibrium. It's not even at the equilibrium, quite at the equilibrium after 50 seconds. And you'll notice that the angular, if you look at the scale, the angular velocity is really small. Because of the large damping, it's like the pendulum is kind of moving through treacle, or that's the British word, what's the equivalent, like molasses or something like that, to get back to the equilibrium point. So it's moving through some very viscous medium, say, or it's a lot of friction in the pivot point. And so it's taking a long time to crawl back to the equilibrium. So that's what you're seeing here. Interestingly, this is an important point about phase space plot. On phase space plot, we don't see the time. So it's not obvious on the phase space plot that it takes a long time to crawl back to the equilibrium, other than the fact that the angular velocities are tiny. So it's kind of crawling back linearly after it initially gets going towards the equilibrium, but at a very slow angular velocity, at a very slow speed, because of the very large damping force. Okay. So now I'm going to move on to adding a driving force into this and looking at some of these plots. So I mentioned that in this class, I'm going to start with a driving force very close to the resonant frequency, the natural frequency. Now I'm going to pull that driving force away from the natural frequency, and that's one way of approaching chaotic behavior. And then in the next class, we'll take maybe the more obvious route, which is to have no driving force, gradually switch it on to create chaotic behavior. But anyway, I'm going to put in a value of alpha 1.5. There's no special reason for 1.5, but if I was to put in a number around 1, that means that the scale of the driving force is the same scale as the restoring force. And so that's all I'm doing here. It's having them similar scales. And then for my example, I kept some damping in there. I kept it in this sort of underdamped regime. I put as 0.25. Again, there's no special reason for that value. I just picked some. My omega f is 0.99. So it's 99% of the natural frequency. So it's very close to resonance. And so that's the key point of where I'm going to start working at, where I'm going to work away from to explore chaotic behavior. So let's run this guide, see what we see. And this is what we see. So when you have a driving force, when you switch it on, there's this transient period where things are changing because of the influence of the driving force. And then you get into a steady state where, it's like the system has forgot when the driving force wasn't there. It's just as if the driving force was always on and you're in that steady state. So the first 10 seconds or so in this slide is that transient period. The remaining 40 seconds is kind of steady state period. You see that after 10 seconds, right, just looks like steady state oscillations in the angle, looks like steady state oscillations in the angular velocity. Downstairs here, this is, again, the phase space plot. So I'm plotting horizontally the angle, vertically the angular velocity, and we're seeing the system evolve from some initial state. It's here. This is actually 0.1 radians for the initial angular velocity. Sorry, the initial angle, I didn't change it. And 0 radians per second for the initial angular velocity. So this is the same starting point as all the previous examples of the undamped and damped pendulum. And then we're just going to evolve. This is the phase space trajectory, just following it around here. And then finally it gets on sort of this kind of smoother oval. And what you're seeing there is likewise the transient period and the steady state period. So that transient period is this wandering around here, and then finally this smooth oval or ellipse is when we get on in the steady state regime. So that's what we're seeing in that situation. I can show you that a little more carefully if I slice the data of theta versus omega that I'm plotting. So I'm just going to plot from 1000 to the end of the time bin. So I've got 2000 time intervals. I'm just going to plot the last 1000 of them. So the last 25 seconds. And so if I do that, we just see that simple ellipse, as if we're just seeing some simple periodic motion that's driven by the driving force. Okay. So let's start moving away from equilibrium. So supposing we make this point, the only number I'm changing is the angular frequency of the driving force, and now it's 10% away from equilibrium. So we'll just run this case. I think I can do this one pretty quickly. And I think I can remove the slicing here. So this is the situation for the driving frequency that's not 99%, but 90% of the natural frequency. There's a longer transient period. It takes longer to get to this steady state where the fact that there was originally no driving force is we've kind of lost that memory of that. So it's not to maybe 15 or 20 seconds now that we see simple periodic behavior in the displacement, simple periodic behavior in the angular velocity. The phase space trajectory here to steady state takes several laps on this diagram, on the phase space diagram. If I was to look at the last 25 seconds on the phase space diagram, by slicing the arrays that have theta and omega in them, we see that eventually, though, we do reach this sort of more simple periodic behavior for this driving force that is now just 90% of the natural frequency. Okay, so I'm going to go to another case. We're going to do a bunch of cases here and just see what happens. So 7.24. So there's going to be some numbers here that say, well, why on earth would he have picked those? I was kind of randomly picking them to try and pick out different features. That's the reason for these. So now we're at 72% or so of the natural frequency. So we're getting a significant distance in a driving frequency from the natural frequency. And I think really I want to look at this guy. So now this is starting to get, more interesting, perhaps. One thing that you can see in the top two diagrams, which show the angular displacement versus time and the angular velocity versus time, is actually that this pendulum is now looping the loop due to the driving force. Because of the phase, the difference in frequencies of the driving force and the natural frequency, this pendulum is swinging over the top multiple times. So if you look at the scale here, so this is radians, right? And there's 2 pi radians in one complete circle. So every time we jump down 2 pi on this plot, so from 0 to 6 point something, the pendulum's looped the loop. And so this pendulum is looping the loop multiple times. It's just swinging round and round and round. In the angular velocity ride, it has this sort of interesting pattern, which sort of has a transient period to it, and then a more periodic period. But it's certainly a much more complicated motion now for the pendulum, and it looks especially complicated probably in this phase space diagram. If I was to look at the last 25 seconds in the phase space diagram, again with the idea, I'm going to remove some of the transient period, right? It's a transient period in here, but after 20 or 25 seconds, it looks like whatever periodic motion there is, it's periodic. It's not sinusoidal, but it is periodic. It seems to reach that periodic motion. Let's see what the phase space plot looks like then. You see this. So it also has converged to a kind of a simple repeating or periodic motion. It's not sinusoidal motion. It's not like this oval that we saw in the last case. It is this more complicated path in phase space, but it keeps walking around this complicated path in phase space. So it'll walk in from the right-hand side over here, loop around here, walk out the left-hand side over here, and then repeat. And then repeat again. And so it's still evolved to some sort of periodic motion. It's just a more complicated periodic motion than just a sinusoidal motion that we saw very close to resonance.